Okay, so we're recording. Welcome back, everybody. This is the last lecture of the semester. This is it. And what we're going to do here is finish up our discussion of Maxwell's equations, in particular, electromagnetic waves. That's the last topic in this lecture. So just to remind you, the final exam is exactly 1 week away. So on Wednesday of next week, that's when the final's happening. And also remember, it's at a slightly different time slot than the lecture, right? Lecture goes 2 to 4, final exam goes 2:15 to 4:45, okay? So if you come in here at 2 and I'm not here yet, don't freak out, it starts at 2:15, okay? Also, the final exam review packet that I distributed, I'm gonna give the answers and the fully worked out solutions. I'll put those up on Canvas on Friday, all right? So, any questions before we jump back into this? Right then. So this is where we left off. We talked about electromagnetic waves and how there's this thing called the electromagnetic spectrum, which basically contains all different types of electromagnetic waves that exist out there in the universe. And we kind of classify these different types of electromagnetic waves in terms of their wavelength. So we've got radio waves, which have the longest wavelengths, and then all the way out to gamma rays, which have the shortest wavelengths. And they're all produced by different processes, but fundamentally, all electromagnetic waves are produced when you have an accelerating charge, all right? So the basic picture you should have is, if I have a charge Q, which is shaking up and down, that's going to send out this electromagnetic wave, which consists of an electric field and a magnetic field, which are both oscillating at some frequency. And that's what this basic picture looks like right here. Okay? So, we derived a whole bunch of equations that describe this type of electromagnetic wave. So the next thing we're going to do is go through an example problem. Okay? So here's the example. We have an electromagnetic wave with a frequency of 60 hertz. So that's actually a really low frequency for an electromagnetic wave. Let's say this wave is propagating in the positive x direction. With this wave, we have an electric field, an E field, that oscillates along the y-axis, and the amplitude of that E field, which we call E naught, is 2 newtons per coulomb. So that means as the electric field oscillates up and down, the peak value that it reaches is 2 newtons per coulomb. So what we're going to do here is derive expressions for the electric field and the magnetic field. So we have E as a function of x and t, and B as a function of x and t. We're going to be able to write down those exact formulas for this wave, okay, given the information here. So the way this is going to start is to remember that for an electromagnetic wave in general, we have E, the electric field, is a function of x and time, so it's a function of both position and time. This is given by E naught, which is our amplitude, times sine of kx minus omega t, all right? So that's the general expression. All we're doing here is coming up with the values of E naught, k, and omega. That's really all we have to do. And similarly for the magnetic field, B is a function of x and t. That's B naught, where B naught is the amplitude for the magnetic field, so it's the maximum value the magnetic field takes on, times sine kx minus omega t. So our job is just to find all the different variables that go into this. Okay, so what are we given? We know that E naught is 2 newtons per coulomb. We also know the frequency F is equal to 60 hertz. And that's all the information we're actually going to need to completely describe the wave, okay? So why don't we start with this? Given E naught, given the maximum value of the electric field, I can figure out B naught, the maximum value of the magnetic field. We derived a formula for this. Do you guys remember what it is? It's one of the last things we did on Monday.
C equals E naught over B naught?
Yeah, so C, what does C represent here? That's the speed of light. for an electromagnetic wave, that's equal to E naught over B naught. So that means I'm trying to find out what B naught is. That's just E naught over C. So that's pretty easy to do. That's just 2 newtons per coulomb divided by C. What's the value of C? 3.00 10 to the 8 meters per second. It's the speed of light. Okay. What does that come out to? Can someone just do that for me? 2 over 3 times 10 to the 8. 6.67, yeah, this is just be 6 repeating, but rounded up to 6.67. 10 to the negative 9, okay? I would agree. And the units here are Tesla, okay? Okay, let's do the next part. I know what F is, but in this expression I have an omega. There's a pretty simple relationship between the two. If I want to know what omega is, what do I do? 2 pi F. That's just 2 pi times F, right? They're both a type of frequency. It's just that F is expressed in cycles per second, so how many times does the wave undergo a complete cycle of oscillation per second versus radians per second. So it's just 2 pi. That gives you the difference between those two. So we have basically 2 pi times 60 hertz, which is the same as inverse seconds. And 2 pi times 60, that's 376.99. We'll round that off to the third significant figure. This comes out in radians per second, okay? Okay, so we have everything we need except for the K value. Okay, do you guys remember how this works, K? K is equal to 2 pi divided by lambda. That's what that is. Where lambda is what we call the wavelength, okay? So, okay, now I need to know the wavelength. How could I figure that out? Well, the speed of light is also equal to lambda times f, okay? That's another thing we derived in the previous lecture. So that means lambda, the wavelength, is the speed of light divided by the frequency, okay? So if you know the frequency, you automatically know the wavelength. That's how this works, because the speed of light is a constant we can always assume. So that means K, which is what we call our wave number, by the way, it's going to be 2 pi divided by C over F, which is the same as saying 2 pi F divided by C, right? So now we can just crunch the numbers. That's going to be 2 pi times 60 hertz, or inverse seconds, that's F, divided by C once again, which is 3.00 times 10 to the 8 meters per second. Okay? And that gives us our wave number K. What does that work out to, everybody? What do we get for this?
1.26 times 10 to the negative 6?
Yeah, it's like 1.26 10 to the minus 6. Units here, so seconds cancel. This is in units of radians per meter. That 2 pi factor introduces radians. Okay, so to summarize, here's what we have. The electric field as a function of x, which is position, and t, which is time, is given by 2.00 newtons per coulomb, that's E naught out in the front, times sine. Now we have K, which is 1.26, 10 to the minus 6 radians per meter, times x. And then we have minus omega, which is this number, 377, basically, radians per second, times time. And what this allows you to do, basically, if you give me a position x and you give me a time t, I can plug them into this, and that tells me what the electric field is, okay? So you need both a position and a time. It's dependent on both of those things. And then same thing for the magnetic field. It's the exact same expression except with a different constant out front for the maximum value of the B field, which in this case happens to be 6.67 10 to the minus 9 Tesla, but then the rest is the same, right? We have sine of, I won't even bother writing it again, it's the same exact thing in brackets, okay? So that's a complete description of this electromagnetic wave. Because you can say what the E field and the B field is at any given position, at any given location, and at any given time. Right? So that's how this works. Any questions on that? Okay, so I'm going to give you a follow-up. Well, it's just a different question, actually. It's not a follow-up, but it's a similar question. Let's say we have this electromagnetic wave, which is propagating in the positive x direction. So the diagram looks the same, except the details are now different. Let's say that we know the expression for the magnetic field. It's this right here. Okay, so I'm giving you the values of the amplitude and k and omega. Okay? So based on that, you should be able to tell me what is the wavelength measured in meters for this wave? What is the frequency measured in hertz? And what is the amplitude of the electric field measured in newtons per coulomb? Okay? So do these calculations. Should only take a few minutes, and then we'll go through it together. Okay? So we're using the same ideas we just used in the last example to make these calculations. So let's see what you get. So what are we getting here? Who's got the frequency? What's the frequency?
1.77.
Okay. Who's got the wavelength? What's the wavelength here? Okay. Pretty straightforward, right? Just go through it real quick. Just so you know, this is what we are given. We're given the amplitude of the B field, which is B naught. That's the constant out in the front, which is 3 times 10 to the minus 4 Tesla. Okay, so based on that, we can immediately figure out what is E naught, right? Because what's the relationship with B naught?
C times B naught?
It's just C times B naught. So we'll take C, which is the speed of light, 3 times 10 to the 8 meters per second, multiplied by 3 10 to the minus 4 Tesla, giving us, yeah, so that's 9, and then the power of 10 is 10 to the 4, right? So it's 9 times 10 to the 4 newtons per coulomb. So that's the maximum strength of the E field that it will reach. All right, here's some other stuff we're given. We're given the value of K. That is exactly 1 times 10 to the minus 10 radians per meter. And we're also given omega, which I'll write up here, is 3 10 to the 18 radians per second. Okay? So we want to know the frequency. Let's just do that real quick. Remember omega, which appears in our formula, is 2 pi times f, which means the frequency f is just omega divided by 2 pi. That's it. So here we go. 3 10 to the 18 radians per second. Just divide 2 pi. Gives you the frequency in cycles per second, which is the same as hertz. And yeah, just like you said, this is 4.77, 10 to the power of 17 hertz. So that's a ridiculously large frequency. Think about that. That means this electromagnetic wave, every single second, undergoes this many cycles of oscillation. Okay, so like 10 to the 17th power, on that order of magnitude. That's how many times the electric field oscillates between its maximum back to 0 and then to a negative value and then back to its maximum. Okay? And then now let's get the wavelength. Because we know that K is 2 pi divided by lambda, then we can immediately solve for lambda. That's 2 pi divided by K. So here we have 2 pi divided by 1 times 10 to the minus 10 radians per meter. So this is going to work out in units of meters. And it's going to be 6.28 times 10 to the minus 10 meters. Okay? So actually, based on this, can anyone guess what type of electromagnetic wave is it? In other words, what part of the spectrum are we in if we have this kind of wavelength? Is this like a radio wave, visible light, something else? This isn't, yeah, this would probably be in the X-ray part of the spectrum, around there. Okay? So very small wavelengths, comparable to the size of an atom. Okay? All right, so we all good on that? This stuff is pretty straightforward. This is just, how do we mathematically describe an electromagnetic wave? Okay? So the last thing we're going to touch on is this. Energy considerations. Okay, so how do we think about energy in the context of EM waves? So the way we do that is using two results that we derived. One was kind of recently, and the other was way back in the chapter on capacitors. So we want to just recall that both electric and magnetic fields contain energy. So that is, if you have some region of space where there's an E field present or a B field present, there's going to be some energy contained in that space. And we could talk about the energy density. That's a common way of talking about this stuff because it gives you a simple expression that only depends on the value of the fields. So the energy density is defined as the energy per unit volume. And we have an expression for E fields and B fields separately. But for an electromagnetic wave, both types of fields are present, right? So we're going to have to consider both of these types of energy density. So let's just review. The electric energy density is given by epsilon naught times E squared divided by 2. So really, the only thing it depends on is the strength of the E field. Stronger E field, more energy density. And same with the magnetic energy density, which we call UV. That's B squared over 2 mu naught. So it's only dependent on the strength of the B field. The rest is just constants. Okay? So, like I was just saying, if we have an EM wave, if we have an electromagnetic wave, we're going to have both an E field and a B field present. And let's just recall what the relationship between the E field and the B field actually is. It's given by this. E over B is equal to C. So the electric field strength divided by the magnetic field strength is equal to the speed of light. So what I'm going to do is just show you real quick, demonstrate, that because of this fact, when we have an electromagnetic wave, the electric energy density and the magnetic energy density are equal. So in other words, there's just as much energy in the electric field as there is in the magnetic field. They're equal. So it doesn't take too much to show that. Let's just do it real quick on paper. Let's start with the formula for electric energy density. And what I'm going to show you is that it's equivalent, if we make a few substitutions, to the magnetic energy density. So this says electric energy density is epsilon naught times E squared divided by 2. Okay? But into that formula, I'm going to make the following substitution. I'm going to say that E is equal to C times B, speed of light times the magnetic field. So what do I have? I have epsilon naught times C times B squared, all divided by 2. Okay, so to kind of expand that out, I have epsilon naught C squared, B squared divided by 2. All right, so into that, I'm going to make another substitution. I showed you guys last time that the speed of light can be written in the following way. It can be thought of as the square root, 1 divided by the square root of epsilon naught times mu naught, like this. So if I have a C squared, it's basically this expression without the square root. Okay? So what do I have? I have epsilon naught, then I have B squared divided by 2, and now I'm going to put in the expression for C squared, which is 1 divided by epsilon naught times mu naught. So guess what? Epsilon naught goes away, cancels here, and then I get B squared divided by 2 mu naught. But that's the same as our magnetic energy density, okay? So, in the case of an EM wave, electric and magnetic energy densities are equal, okay? That's an important thing to know. Okay, so we've proven that fact. So there's a few other things I want to demonstrate here. When it comes to the total energy density, there are various ways we can express it, okay? We can express it purely in terms of the E field, purely in terms of the B field, or using some kind of combination of the two. They're all equivalent expressions, but depending on the situation, it might be more useful to use one or another, okay? So when we talk about the total energy density, that's nothing more than the sum of magnetic energy density and electric energy density. So let's do a quick derivation of those different expressions, which I'm going to show on the slide in a second. Okay, so the total energy density, which I'm just going to call U, is equal to UE plus UB. Okay? But since these are the same thing, I can write it as 2 times UE if I wanted to, right? So in other words, I can write it as 2 times epsilon naught E squared divided by 2, which is just get rid of the 2, epsilon naught E squared. Okay? But another way I could think about this is, well, if these are the same thing, I could just write it as 2 times UB. Right? That would work as well, because I have 2 of the same term. So in that case, what I would have is 2 times B squared divided by 2 mu naught. Get rid of the 2, what's that? B squared divided by mu naught, like this. Okay? So that is an equivalent way of writing it. Okay, so these are 2 expressions. I'm going to show you just one more way of writing this. All right. For this, I'm going to start off with epsilon naught times E squared. okay? Again, we just showed that that's a way of writing the total energy density. But instead, in this case, I'm going to take E squared and just separate that out into two terms. E times E. So it's epsilon naught times E times E. Okay, now for one of those E terms, I'm going to sub it out with the following. I'm going to say B divided by C. We agree we can do that, right? The electric field is just the magnetic field. Yeah, divided by C, right? Oh, I'm sorry. What am I doing? It's multiplied by C. Yeah, my bad. Okay, so okay. Forget what I just said. It's the magnetic field multiplied by C. Yeah. Okay. Anyway, so we have epsilon naught, we have E, and we have B. And then I just want to remind you that C is 1 divided by the square root of epsilon naught times mu naught, right? That's an expression for C right there. So if I kind of collect everything that's here, if I have epsilon naught divided by the square root of epsilon naught, that's like having the square root of epsilon naught on top, and then I have the square root of mu naught on the bottom like this, okay? And then all that's multiplying that is E times B. So yeah, that's what I wanted to get to right there, all right? So all three of these expressions work, just depends on what information you know as far as which one you want to use, okay? And it's the magnetic plus the electric energy density giving you the total energy density in the wave. All right, so yeah, any questions on that? It's just some algebra, right? So here are the results. Okay, we can write this as epsilon naught times E squared. That works. We can write it as B squared divided by mu naught, or the last one we just derived was square root epsilon naught divided by mu naught times E times B. Any of these will work. Okay, so here's one for you to work out, okay? We have an electromagnetic wave. And let's say that for this electromagnetic wave, the maximum value of the total energy density is 1 joule per cubic meter. So keep in mind, this is a quantity that's going to be changing because the E fields and the B fields themselves are changing over time. But we're just saying that this is the maximum value for the energy density, okay? So based on that and that alone, you should be able to tell me what are the amplitudes of the electric and the magnetic field. So you should be able to tell me what's E naught, what's B naught, using the formulas we just derived. So take a few minutes to work it out, and we'll go through it together. So, any answers? What's E naught?
3.36 10 to the fifth.
Okay, good. What about B naught?
1.12 times 10 to the negative 3.
Yep, that's right. So there are about a million different ways you could go about doing this one because we have all these formulas, but I'll just do it this way. We have the total energy density of our wave equaling epsilon naught times E squared, right? So from what I'm interested in is the maximum value of this thing. I'm going to plug in the maximum value of the electric field, of course. And to solve for that maximum value of the electric field, that's just going to be energy density max divided by epsilon naught under the radical like this. Yeah. Oh, sorry. There you go. Right, so we have 1 joule per cubic meter, and then we divide out epsilon naught. You guys remember what the value is for epsilon naught? 8.85, 10 to the minus 12. Units are weird. Coulombs squared divided by Newton's meter squared like this. So just take this all under the radical. And what you get is just what Zachary said, which is 3.36, right? 10 to the 5 Newtons per coulomb. All right, now that we have that, we can just go ahead and probably get B naught the easiest possible way, which is, here, I'll move this up, like this, okay. Probably the easiest way to get B naught is just to say it's E naught divided by C, right? So just take our previous result of 3.36, 10 to the 5 Newtons per coulomb, and then divide out C, which is 3, 10 to the 8 meters per second, and that gives you 1.12, 10 to the minus 3 Tesla, okay? So we know the energy density, we immediately know what the fields are, okay? Any questions on that? Okay, so continuing this sort of discussion of the energy that's contained in electromagnetic waves, let's be a little more specific. Not only is energy contained in electromagnetic waves, but that energy is going somewhere. That energy is propagating from one place to another, right? Classic example of this is the sun, right? The sun is depositing energy onto the Earth through electromagnetic waves that it's sending through space towards the Earth. All right, so if you want to get a better handle on how that energy is flowing through space when you have an electromagnetic wave, we want to define a new quantity, which is called the pointing vector. All right, this is pointing, not spelled as you're pointing in some direction, it's someone's name pointing, okay? Anyway, the variable that we use for the pointing vector is a capital S, okay? So I'm going to define what this vector is for you, both in terms of the magnitude of the vector and the direction of the vector. What is each of these things telling us? Okay, so the basic definition here is the pointing vector gives you the energy of an electromagnetic wave going through a surface per unit time per unit area. So this is the picture we should have in our mind. Let's say we have an electromagnetic wave like this, and let's say it's traveling to the right in this picture. So we can put up a little surface that the electromagnetic wave is going to hit. It's going to hit this surface head on, right? And it's going to be going through the surface. So every time, every second, let's say, every hour, every minute, whatever we want to use for time, there's going to be some amount of energy going through the surface, right? That's what we're going to call U, just the energy that travels through that surface. Then, if we divide out the area of the surface, which is A, and we divide out the time interval, delta t, then we get this thing called the pointing vector, okay? So the units, by the way, are watts per square meter. Let's try to think why that might be the case. You guys remember what a watt is defined as? Yeah, a watt is defined as a joule per second. So the energy going through the surface, that's going to be measured in joules. The time interval is going to be measured in seconds. And when we combine joules per second, we get watts. And then, of course, the area part is going to be given in square meters. So that is how many watts are hitting the surface per square meter of that surface. Okay, that's what it is. All right, so that's just the magnitude of the vector, by the way, right? I haven't discussed anything that involves the direction yet. So how do we think about the direction? Well, the direction is simply the direction that energy is moving in, right? This electromagnetic wave is carrying with it some energy, and the direction that energy is moving in, that's the direction of the pointing vector. In other words, it's just pointing in the direction of the wave's propagation. Okay, so in this case, if we have a wave moving to the right in our diagram, then the vector S is going to be also pointing to the right. Okay, that's the idea. So the next thing I'm going to do is a short derivation of how we can actually calculate this thing called the pointing vector in terms of the E fields and the B fields. Okay, and we're going to derive this result right up here. So here's how this goes. Starting with the basic definition that S, this is called our pointing vector, is equal to some kind of energy per unit time per unit area traveling through a surface. So I'm going to copy down the basic picture that was on the slide just so we can use it for reference. Let's imagine our surface is just some kind of rectangular surface like this. And let's say the area right there is A. And what we have is some kind of electromagnetic wave which is coming in and just hitting that surface. Okay? Let's also label right here that the surface has some kind of length to it. Okay? Now, how do we want to think about this length? Well, of course, the longer we wait, or the longer the time interval we consider, the more energy is going to pass through the surface, right? That stands to reason. Another way of thinking about that is the more time we let go by, the longer this length will be, okay? Because that length can be thought of as just the speed of light c times the time that passes, okay? That makes sense? This length is just the speed of light times the time that passes. So we take this basic definition and then just, again, write it in terms of variables. We have energy, which is capital U, divided by area, which is A, divided by time, which is delta T. Okay, so now what I'm going to do is just focus on the energy part that's at the very top, because we have everything we need to be able to deal with that, okay? So energy density, remember, that's energy per unit volume. That's lowercase u. Total energy, that's uppercase U, okay? How do I go from one to the other? I just multiply by the volume, okay? So here, let me just put in words what this equation is saying, because it kind of looks like it might not make a lot of sense. This says energy is energy per unit volume, right? Times volume. That's all it says. Okay? But the thing is, actually, let's go to another line on this one. The energy density, the energy per unit volume, is something we already have a nice formula for. Okay? And I'm going to bring that into play in a second, but for now I'm just going to write that as lowercase u. But looking at this picture here, what can I say the volume is equivalent to? What is the volume of that little, basically, space that I've constructed here? Yeah, it's just A times L, right? So if I take my energy density times A times L, that should be the total energy. And then, as I said just a second ago, L is C times delta T. So what do I have? I have energy density times A times C times delta T. That's what I've got. That's the total energy contained in this box. That's what that is. All right? So that means my Poynting vector S is this energy, which again is energy density times A times C times delta T. And then what do? I divide that by A and I divide that by delta T, just given the definition, right? So the area drops out, the time interval drops out. It looks like this is nothing more than the energy density times the speed of light. Okay? And for the energy density, I'm just going to pull out the result we just derived. This right here is the square root of epsilon naught divided by mu naught times E times B. And then C, that's the same as 1 over the square root of epsilon naught times mu naught, right? So what can we do? We can cancel out the epsilon naught factors here and here. And if I have mu naught in the square root twice, that's just the same as mu naught. So in other words, this is just EB divided by mu naught, okay? All right. So that's one derivation we wanted to get a handle on. Okay, there's one little wrinkle to this. Oh, go ahead. Yeah, what's up?
The lowercase u, that's the total energy density, right? Not the-
Yeah.
Not the one that.
This is the total. Okay. So there's one wrinkle to this, which is that E and B, those are both things that are going to be rapidly changing over time, right? They oscillate up and down very, very quickly. So most of the time, we're not interested in what's called the instantaneous value of this quantity, because it's just changing way too quick for any kind of instrument to detect, right? I mean, think about trying to measure the oscillations of visible light, right? You'd have to be taking trillions and trillions of measurement every second just to get that right. So usually what we're interested in is just an average, okay? So I'm going to explain how we can go from this, which is like an instantaneous value, to an average, which is realistically what you're going to actually measure, okay? All right, so here we go. Basically, in this expression, I have 1 divided by mu naught, and then that's multiplying E, and that's also multiplying B. I'm just going to remind you that E is some kind of amplitude E naught times sine kx minus omega t. And then B is some kind of amplitude B naught times sine kx minus omega t. So in other words, if we collect all the constants out front, it's E naught times B naught divided by mu naught times sine squared of kx minus omega t. Okay? So again, if we want to take the average, essentially what we're doing is we're taking the average of this sine squared function, okay? And does anyone know, if I take the sine squared function and I just take a look at its average value, what do I get? What's the peak value of sine? 1. So the average value of sine squared turns out to be 1/2. Okay, I'm not going to prove that for you here, but the average of this guy, if you average over many, many cycles, is 1/2. Okay? So that means the average of our Poynting vector is just this constant out front, E naught, V naught over mu naught, but with a 1/2 factor, so with 2 mu naught on the bottom. All right? So this is typically what we care about because, again, things are changing so rapidly that we are often just measuring an average. All right? So those are the derivations I wanted to show you. And just to recap, we have this thing called the Poynting vector. It tells us how many watts per square meter are going through some kind of surface when an EM wave hits it. So the instantaneous value is given by this. It's actually E crossed with B over mu naught. Remember, I said this is a vector, it has a direction. What I derived is the magnitude of it. To get the direction, you have to actually consider this to be a cross product of E and B, okay? But again, because EM waves oscillate very rapidly, we just want the time average value, averaged over many cycles, and that is the same expression, but we have our amplitudes E naught and B naught, and then a factor of 2 on the bottom, okay? So, by the way, has anyone heard of this kind of term, intensity of a wave? Okay, this average value is also sometimes known as the intensity, okay? So if you ever see, the intensity of the wave is such and such, this is what it's referring to, okay? All right, so a lot of derivations. Let's do an example, okay, to make some sense out of this. So this is a good example to go through because it's really practical. We're talking about the energy of sunlight that is hitting the Earth. Okay, this is what allows all life on Earth to exist. So let's try to put some numbers to it.
This picture is wrong. Why is the dark side of the Earth facing the sun?
Huh?
The picture is wrong. Why is the dark side of Earth facing the sun?
Don't worry about that. Yeah, I didn't notice that actually. Yeah. Okay. Here, check this out, guys. We're gonna quickly fix that. There, like that? That better? All right, there you go. So here's the problem. The intensity of sunlight hitting the Earth is about 1,350 watts per square meter. Okay, so for every square meter patch, okay, that we can draw, that sunlight can pass through at the location of the Earth, that's how many watts are passing through it. All right, here's what we'll do. We're going to find the amplitude of the electric and the magnetic fields, E naught and B naught, at the location of the Earth. We're going to find the maximum energy density of each of these fields. Okay? And then we're going to answer this following question. We have the Earth absorbing approximately 70% of all the radiation from the sunlight. So 70% is absorbed by the Earth. The other 30% basically goes back into space. It just reflects right off the atmosphere of the Earth. So based on that, how much energy in total does the Earth absorb from sunlight each day? Okay, so how many joules of energy are we absorbing through sunlight every single day? To answer that last question, we're going to need to know the radius of the Earth, which is right here, 6,370 kilometers. Right? Okay, so let's do this. So when we're given the intensity, remember that's referring to the average value of our pointing vector. Okay? That's what it means. And as we just derived, that's E naught times B naught divided by 2 times mu naught. Okay? I don't know what either one of these fields actually is for the time being, so I'll just make a substitution. Let's say that instead of E naught, I'm going to write this as C times B naught. I'm able to do that, right? Just multiplying by a factor of C gives me the other field. And then that's multiplying B naught right there, and then I have divided by 2 times mu naught on the bottom. So let's say I want to solve first for the magnetic field strength. That's B naught squared. Okay? Well, if I multiply by 2 mu naught on this side, I'm going to have 2 times mu naught, and then S average, and then I have to divide out this C term, and then I've got B naught squared. So if I square root that guy, I'll have B naught. All right, cool. So B naught is the square root of 2 times mu naught, which is 4 pi times 10 to the minus 7 Tesla meters per amps. S average, that's the intensity of the sunlight. So at the location of Earth, that's 1,350 watts per square meter. And then we'll finally divide by the speed of light, which is c, which is just 3 × 10⁸ meters per second. Okay, so we crunch these numbers, and what we get is a relatively weak B field, actually. It's just 3.363 × 10⁻⁶ Tesla. Okay, so rounding that off, it's 3.36 × 10⁻⁶ Tesla. Okay, so that's the amplitude or the peak value of the B field in the electromagnetic waves coming from the sun hitting the Earth, all right? The peak value of the E field is just that times C, remember? So E naught is C times B naught. So we'll take 3 × 10⁸ meters per second, and we'll multiply by this, which is B naught, 3.363 × 10⁻⁶ Tesla. And that's going to give us what we want. Works out to just a little bit over 1,000. 1,009 if you work it out, newtons per coulomb. But rounding it off and putting it in scientific notation, it's about 1.01, 10 to the third power newtons per coulomb. Okay? So there it is. All right, so that's the field strengths, basically. Now, let's look at energy density. So we have formulas for this. Electrical energy density, we just want that part, is 1/2 times epsilon naught times E squared. Okay, so we can put a number to that. It's 1/2 times epsilon naught is 8.85, 10⁻⁻12 coulomb squared per Newton meter squared. Okay. Then we're going to plug in our value of the electric field strength at its peak, which is 1,009 newtons per coulomb. And we're going to square that whole thing. All right, you can work this out. It's actually a relatively small energy density. It's only 4.51 10⁻⁶ joules per cubic meter. Okay? So I can answer the other question, what is the magnetic energy density, without doing any kind of calculation. What is that going to be? Yeah, because we know that for an EM wave, electrical and magnetic energy densities are equal to each other. So I don't need to do the calculation again, it's just the same thing. Okay? So this is telling us that we just sort of stand outside and let some sunlight hit us. The energy density contained in the E and B fields of those electromagnetic waves hitting us from the sun are these values right here. Okay? All right, so any questions so far? There's one last part of this that we want to answer. The last part of this that we want to answer is, every single day, how much total energy is the Earth absorbing from the sun? Okay? So for that, we're going to go back to the most basic definition of the Poynting vector S. Okay? So if we recall, the Poynting vector is just the energy per unit time per unit area passing through a certain surface. Okay? So in this case, we're talking about U, I'm going to just write U for the energy, A for the area, and delta T for the time. Okay? Now, I'm trying to solve for the total energy, so that's what appears on the top of this expression. So U is equal to S times A times delta T. Let me just remind you that we already know S. That's, in other words, the intensity of the sunlight hitting the Earth. It's 1,350 watts per square meter. Okay, what's delta T? That's going to be 1 day. We're interested in how much energy is being absorbed over the course of 1 day. Okay, so in order to do this, I have to change units. It's not too hard to do. I just want to take 1 day and convert that to what unit? Seconds. All right, how do I do that? There's 24 hours in 1 day. Cancel out days. Okay, there are 60 minutes in 1 hour. Cancel out hours. And then finally, there are 60 seconds in 1 minute. Cancel out minutes. All right, so we've got 24 times 60 times 60. And if you work that out, that's 8.64 times 10 to the 4 seconds. So that's the relevant time interval since we're interested in 1 day. Okay, what about the area? So I have the intensity of the sunlight, I have the time interval that we want to consider. Now I have to think about the area. So what should I use here? Now, so we want to use an area formula, not a volume, but which one do we want to use?
Surface area.
So do we want to use the entire surface area of a sphere?
Yeah.
No, for what you pointed out, right? There's a dark side of the earth that the sunlight is not hitting, right? So yeah, there's only a certain portion of the earth that's actually exposed to any sunlight, right? Effectively, what is the area of exposed earth? Surprisingly, it's just pi r squared. It's just pi times the radius squared. Let me try to convince you of that, okay? So right here, this is the earth. It's hard to draw a sphere, but this is meant to indicate a sphere, okay? Now, we have some sunlight coming in. These are rays of sunlight coming in like this, okay? So our question is basically, effectively, what area these rays of sunlight actually see? Well, you can imagine putting a circular surface, so this is now a circular surface that the sunlight rays are hitting head on, and it has the exact same radius as the earth, right? So we'd agree, right? Every bit of sunlight that goes through this little circle is eventually going to hit the earth, right? So effectively, the area that we care about is that of the circle, and that's just pi r squared, okay? So that's how we account for the fact that sunlight is only hitting one side of the earth, and it's not hitting all parts of the earth head on, okay? So let's put a number to that area. So that area is going to be pi times the radius of the earth, which is 6,370 kilometers, but I'm going to put that as 6,370 times 10 to the 3 meters, and we'll square that. So can someone tell me what that area comes out to? You're going to need this number. Yeah, this comes out to 1.275 10 to the 14 meters squared is what I'm getting, okay? All right, so now we're ready to calculate the total energy that is hitting the earth, okay? So that's going to be S, which is this value right here. It's 1,350 watts per square meter, or we could write this, because a watt is a joule per second, I'm going to write this as joules per second per square meter. And then our area right here is 1.275 10 to the 14 meters squared. And then our delta T, that's the time interval, that's 8.64 10 to the power 4 seconds. So you see meters squared cancel here and here, seconds cancel here and here, and we just get joules, right? Okay, so this comes out to, if you do the math, 1.487, 10 to the 22 joules. So that's how much energy is coming in every single day and hitting the Earth. But remember, only 70% of that actually ends up getting absorbed by the Earth. So if we just take that number and multiply by 0.7, okay, that's the amount of energy in sunlight that the Earth is actually absorbing every day, okay? So can someone do that last part? Just multiply that by 0.7. 1.04, 10 to the 22 joules. That's what we get to play with each day as far as like all of the life on Earth is concerned. That's where the energy is ultimately coming from, okay? So any questions on how we did this? All right. So we're getting pretty close to the end here. I have a couple conceptual questions for you guys to work out, okay? So the other side of this is that the Poynting vector, which tells you basically how many watts per square meter we're dealing with when it comes to an electromagnetic wave, it has a direction to it, okay? And that direction is given by the cross product of E and B. So in other words, if you take E cross B for your electromagnetic wave, the result of that is going to give you the direction the wave is moving in. It's going to give you the direction the wave is actually traveling in. Okay? So I have three different examples here, which show you the E and B fields for a certain type of electromagnetic wave. So given that you know the direction of E and B in each one of these cases, you should be able to tell me which way the wave is moving, which way is it propagating in each case. Okay? That's just the right-hand rule because we're dealing with cross products. So work it out in each case, take a few minutes, and then let me know what you get. All right, so if you're not doing the right-hand rule, you're not doing the problem, so let's just see some of this. All right, what are we getting for this first case right here? Okay, that's the positive z direction, right? Let's just verify. Okay, if I do E like this, okay, that's the first vector, so point the fingers of your right hand in the direction of E, cross them with B, that means you point your fingers up, now your thumb is out of the page, so you got that right. What about in the second case? Down. All right, so let's verify that that works. In the second case, I've got E, and then in order to curl my fingers out of the page, I need to orient my hand like this, with my thumb pointing down. So you got it right. Okay, what about this last case here? So the right, okay? So in this case, this is showing me E is going into the page. So point right hand fingers into the page, then curl them up like this, and then B is going to the right. The direction of the wave is going to the right, okay? So if you know the E fields and B fields, you can determine which way the electromagnetic wave is moving in, okay? All right, so I'm actually gonna take this result right here and apply it to something that you might not expect to even be relevant at all, okay? So consider just the simplest circuit in the world. We have a battery here, and then we have a resistor here. And then there's some wires that connect the two, okay? So we know that the energy that gets dissipated in the resistor is ultimately coming from the battery, right? But let's be a little more specific. Like, how is the energy moving around? You might guess that the energy is sort of just moving through the wires from the battery and then to the resistor. That would be the first thing we would think of, right? But that's actually not true, okay? The energy, surprisingly, is actually just moving through the empty space between the battery and the resistor, okay? And the way we can show that is by using the pointing vector, because remember, the pointing vector tells us how energy is flowing. It's telling us, in particular, if we just take the cross product, what direction is energy flowing, okay? So what we're going to do is show the E field and the B fields in this circuit, and we'll show which way energy is flowing. Yeah, go ahead.
So the electrons that are moving through the wire, their energy is the one that's going through the free space?
So you need, here's the way to think about it, okay? You obviously need the motion of the charge, the current, to create a B field, right? And you also need the charges to sort of arrange themselves on the wire in a certain way to create the E field. But the point is, it's those fields that carry the energy and not the charges. And that's what we can verify by doing this, okay? So we're going to put on this diagram to start off what the E field and the B field looks like at various points, okay? So for the E field, this is what it looks like. So you should already know this from previous chapters, but I just want to remind you. Okay, inside of the battery, which way does the E field go? Well, basically, it just goes from the positive terminal of your battery to your negative terminal. So inside of the battery, we have an E field pointing down, right? But we also know what the flow of conventional current looks like in this circuit, right? That's going to be basically flowing clockwise in this diagram. So we know that inside of the wires, okay, not inside of the battery, but inside of these wires, that the E field just goes with the conventional current. Remember that? So this E field is what is actually pushing the charges along so that they circulate and create an electrical current. So the E field in the connecting wires, we're assuming the connecting wires have some resistance, but it's pretty small, right? If that's the case, we get a pretty small E field within the wires. But inside of the resistor, okay, the E field is still going the same way, but it's larger because that has a bigger resistivity. Okay, so that's the basic picture of what the E field looks like. So it's going clockwise all throughout the circuit, except it's going the opposite way inside of the battery, and it's a bigger strength where the resistor is. Okay? What about the B field? What does the magnetic field look like? You guys remember? If we have some kind of current, how does the magnetic field direction relate to the current? It loops around the current, right? And in particular, it's given by the right-hand rule. So for example, let's say I'm just looking at this branch of the circuit right here. Current is going up. So my B field lines must be looping around those wires in this sort of way. So over here, you'd see it coming out. And then over here, you'd see the B field going into the page, right? Let's do the same thing, let's say, I don't know, down here. Okay, the B field is going to loop around the wire like this. My current is going that way, so my B field is given by the curl of my fingers on my right hand, coming out of the page over here, going into the page over there, right? So basically, in this region, on the inside of the circuit, we have the B field going into the page, and then on the outside, we have the B field coming out of the page. So that's just from the right-hand rule. That's how the B field loops around the wires. Okay. So check this out. Now that we know both what the E field and B field looks like in a general sense, we can get a handle on the Poynting vector, which again is telling us how is energy flowing within this circuit. So let's do a few examples. We want to do E cross B. If we do E cross B, that gives us the direction that energy is flowing in, right? So I don't know, let's take this as an example, right? Let's say we're right next to the battery, but just to the right of it like this, okay? So how does E cross B work? It's going to be E field, that's with your right hand going down. And then this B field is going into the page, so I'll have to cross into the page. It looks like my energy is going this way, right? That's not along the wire, right? Okay, what about, I don't know, over here? Let's try that, just a random example. So we're going to do E crossed with B. Let's do it on this side first, right? So E going to the right, as shown with the blue arrow, crossed with B going into the page. That looks like it's kind of going into that wire, doesn't it? And actually, if we do the same exact thing up here, it's going to be going down. So it looks like the energy is being kind of eaten up by the wires. That makes sense. The wires have some resistance. They eat up a little bit of the energy, right? All right, what about where the resistor is? So the E field's going down right here. I don't know, let's take this side as our test case. So we have E going down, crossed with B. Looks like energy is going into the resistor. So if you do this a few more times, you can build up this kind of picture, okay? So remember, blue, that's the E field. Red, that's the B field. Now in green, I'm showing you S, which gives you the direction at which energy is flowing in. All right, so what you can clearly see here is the S vector is flowing out of the battery. That makes sense. Energy is going away from the battery. Where is it going? It's going mostly towards the resistor, okay? But because we have resistance in the wires, there's also some energy going towards that as well, okay? But if you think about it, this vector S is definitely not just going along the wire, okay? The energy is flowing through the empty space where you have E and B fields between the battery and the resistor, okay? So again, it's not to say that the flowing charges don't make a difference or they don't matter. It's just that they create these fields, and ultimately it's these fields that carry the energy.
So if you had a big enough circuit, would the resistor, I guess, be receiving energy at a relatively fast speed then? Like if it was like, if you had like I saw that Veritasium video.
Yeah.
You know, but would that be a similar principle? Like if you had it like a meter apart, but the circuit was like really far out to the sides, instead of traveling around the circuit, it would basically reach across.
Yeah, so yeah, exactly. Like how long does it take between when you like hook up the battery to when the resistor starts receiving some energy? Like let's say this is a battery powering a light bulb, for instance, right? It's basically just limited by the speed of light. How quickly can light travel from here to here? Yeah.
What if like this circuit was in like, what if there was more, like if there was more light bulbs, say like it was parallel with the energy, like?
Yeah, so then if you did the same game, you would see that energy is flowing into each one of those bulbs.
Would the energy be the same, like throughout all those light bulbs, or would it?
Not necessarily, because even we showed that, you know, the amount of power consumed by a bulb depends on how it's connected, whether it's in series or parallel, yeah. But anyway, this is just showing the energy flow. Yeah, there's a great Veritasium video, if you guys ever check out that YouTube channel, Veritasium, about this exact topic, so.
They had to do a two-part because the first
Yeah.
part, too many people were arguing.
Yeah, this video caused a lot of arguments, but I'll tell you that he's basically getting this right, in my opinion. Okay. All right, so obviously a really important practical use of all of these ideas we just talked about is wireless communication. And I mean this in the broadest sense possible. Everything from radio which is broadcast from towers and you receive it in your car or your home, to cell phones, cellular networks, to TV, to Wi-Fi. These are just all different types of wireless communication. And they obviously have their differences. If you're an engineer, you care about these differences. But from a physics perspective, they all more or less work the same way, okay? So big picture, what is wireless communication? You have some kind of transmitter and you have some kind of receiver. So what does the transmitter do? The transmitter creates in some sort of antenna, which is used to broadcast the signal, some kind of alternating current. All right, and if the alternating current is at 60 megahertz, then the electromagnetic wave that gets sent out, guess what, is also going to be at 60 megahertz. So basically, whatever the frequency of that alternating current you have, you'll get the same frequency for the electromagnetic wave that gets sent out. And if you give some complicated mix of frequencies, then you can store some kind of message or information within that signal, okay? All right, so from the transmitter, we send out an EM wave, which contains all the information that we're trying to sort of encode, and that moves at the speed of light. So then that gets received by your receiving device, okay? This could be the radio tuner in your car or your phone, whatever the case may be. What's going on in that device? Well, there's some kind of circuit in that device which is sensitive to that particular electromagnetic wave. It's specially tuned so that it's sensitive to whatever that frequency is, okay? And so what you do is when the electromagnetic wave hits it, is it causes alternating current to start flowing in that receiving device. And that's how you pick up the signal, okay? So, of course, each device is going to operate within its own narrow band of frequencies. Like each radio station operates in a certain narrow range of frequencies. Each cellular device has its own narrow band of frequencies. So your receiver has to be specially tuned to some specific frequency or narrow range of frequencies. So there's ways of doing that. We don't have time to cover it in this class, but you can read about LRC circuits, which is how you kind of tune a circuit so it's sensitive to just one frequency, okay? When you turn the dial on your radio, at least in really old-fashioned radios, it's basically just a little LRC circuit with an inductor, a resistor, and a capacitor, okay?
This is slightly tangential, but I heard that there are, like, in relation to that, like, radio waves, that there are some, like, for, like, transmitting radio, there are some frequencies that, like, you're not allowed to transmit on because it would interfere with, like, air traffic control,
Yep.
government, military stuff.
So yeah, obviously this cannot be sort of an anything goes type situation because we need certain frequency bands dedicated for certain purposes, which means, some of them are ruled out or you shouldn't be transmitting at those frequencies.
Yeah, I heard it's the really low frequencies, like the really low frequency they reserve for some stuff.
Yeah, so that is true. All right. We've got some practice problems here. Are you in the mood for this? You're just ready to call it a day. All right. Let's call it a day, huh? All right. That's the end of the semester, everybody. So I'll see you in 1 week for the final.